alternating series test. Okay, first let's look at what we mean by an alternative series. Okay, so alternating series is any series which can be written in one of the following forms, this form or this form. Okay, in this form, here you have negative 1 to the power k and here 1 plus k. Both situations this is a positive series, no? So ak is positive, so you can put any formula for positive series here. Okay, so if you look at here, if k is 1, I get here 1, negative 1 to the 1, negative, no? K is 2 or even power positive, then again k equals 3, I get a negative. So that's why we call this alternating series, no? It's switch between one positive numbers and negative numbers. 2, A4, A6, those even number terms are positive. On odd numbers terms negative, 3, 5, 7, like that. This guy is the opposite, no? This one is positive on odd numbers like 1, 3, 5. For example, if I plugging in k equals 1 here, I get negative 1 to the 2, no? 2 is positive, so 1 is positive. Likewise 3, 5, 7, those are positive, and even numbers negative, no? For example, if I plug in 2, 2 plus 1, 3, negative 1 to the 3. So here even number terms are negative, odd numbers terms are positive. Here odd numbers negative, even numbers terms positive. So in both cases series alternate between positive and negative values. Okay, that's why we call it a alternating series. Now we'll go over alternating series test. Okay, so this either form converges if these conditions are satisfied. Here, soon as I say alternative series, these are positive terms, no, according to our definition. Additionally, limit of ak have to go to 0, no? AK is a decreasing sequence, that is, this is getting smaller and smaller. Okay, so if this AK is a decreasing series, and this one also this limit is going to 0, then this alternative, according to this alternative test, this series converges. Okay. Okay, but along not satisfying the hypothesis of alternating test is not sufficient reason to conclude that the series does not converge. Okay, this theorem says if the series conditions are satisfied, then the series converges. Okay, okay, if the conditions are not satisfied, test is inclusive. Okay, so actually we cannot apply the test, no? So if these conditions are not satisfied, we cannot apply the test. But remember one thing, in case if this AK is not going to 0, then I can say this is divergence, that from the divergent test, no? Because this have to go to 0. If it's divergent, this limit has convergent, this limit has to go to 0 from divergent test. Okay, so if this not 0, divergence test says series diverge. Okay, that is not from the alternative series. Okay, so so these two have to be satisfied for alternative series. Now let's look at example. Okay, so we are asked to decide the convergence of this series. Soon as this negative 1 to the n, we see this negative 1 to the n power, we can think of alternating series, no? Because that is the only thing we learn to handle this situation. So okay, let's look at examples. So this one we need to decide whether it's convergence or diverges. Okay, so this negative 1 to the power, the negative 1 to the power exponent n give us a hint that we might have to use alternative series here test. Okay, so let's try to identify the term. Okay, so here to apply the standard form of the alternative series is this, no? We are having this an is 1 over n, which is positive, no? Only condition we need this to be positive, so it is positive, and I have minus 1 to the n. Okay, now we will have to test for the condition. First thing is limit, no? First thing is limit. Okay, so series can be expressed as this, okay, where a is 1 over n, that part is done. So the limit is 0, so the first condition is satisfied, and we have n plus 1 is ak plus 1, no? And this is ak, so series is decreasing. Okay, we can clearly see this is less than this, so series is decreasing. Because of that, from alternative test we can say series is convergent. Okay, so you have to first compare it with the standard form and identify ak term, no? After that we can apply the alternative series test. Okay, let's look at another example. Okay, so we have to determine whether this series converges or diverges. Okay, by the look of it, one might not think this will go for alternative series, but if you think pay little bit attention to this time term, is kind of oscillate, no? So let's look at few terms to get a better grip. Okay, we look at this table. For each k value, sign oscillate from 1, 0, negative 1, 0, 1, 0, like that, and then these are the log terms. We can get the series by multiplying these, no? Just multiplying this and this, this and this, this and this, like that. You multiply these terms to get the series. Okay, so if we expand the series, it will look like this. Okay, so now to tell whether this is convergent or not, I have to look at this sum, no? But the thing is, these zeros, even though they are terms of the series, they are going to have not going to have any effect on the sum. Okay, so we can just concentrate on this positive and negative term to decide the sum. So one thing you can see, in this L1, inside L1 you have odd numbers only, 1, 3, 5, 7. Also this denominator you have odd numbers, no? Then here odd terms stay positive. If I forget about zeros and I think of a new series containing of this is being 1 first term, this is being second and third and fourth, odd terms stay positive, no? Term 1 and 3 are positive, term 2 and 4 are negative. So the new series will have one thing, I can say this form, no? Negative 1 to the n plus 1 form, because I want odd terms to be positive. See here, first term and third term positive, fourth term, second term and fourth term negative. Then to get this odd numbers, you can use 2k minus 1, no? So when k is 0, you get 1. Sorry, k is 1, you get 1. K is 2, you get 3. So I send k from 1 to infinity. If k is 1, I get 1 here. K is 2, 2 times 4 minus 1, 3, no? And like that. So this 2k minus 1 guarantees. Okay, now this is a new series, but both of them have the same sum. Okay, so if I can prove this guy converge or diverge, this guy will have show the same behavior, because this zeros is not going to have any effect. Okay, so we will work on this series now. Okay, so we can express it this form. Okay, that new series I can express it in this form with ak being this guy. Okay, we have to look at its limit and also whether it's increase or decrease. Okay, first we will show this is decreasing. Okay, for that we will use the derivative method. Okay, we will embed this one in this function. We can embed this one in this function. Therefore, if this decreases, also the sequence decreases. No, so we take the derivative of this guy, f dash derivative. Right? Here we can use the quotient rule. No, quotient rule, denominator squared, then first term times the derivative, sorry, denominator times the derivative of the numerator minus derivative of the denominator 2 times the numerator. Okay, here I can take the common factor 2x minus, here I can just cancel these 2x minus 1s, no, and pull out a 2. I can simplify this guy to this. Now this x minus 2x minus 1 is anyway positive for this interval. No, I only want it to be positive in a interval starting value from x. This is positive for all x, but we are interested in this interval is positive, that interval, and then this one is negative for all x bigger than e plus 1 over 2. It's fine. No, if the sequence tail negative, it's enough. Tail is decreasing, is enough, because first few finite terms not going to make a change. Okay, so because of that we can say where f dash is negative for these x values. Okay, because this is negative and this is positive, and then it's decreasing for all x here. No, then the sequence also decreasing for n greater than this time. Okay, all k bigger than this value is fine. Okay, because I said if the condition holds for tail, it works. Okay, now I want to show this is, I need to find the limit. Okay, so let's go ahead and show this limit is 0. Okay, so if I take limit k to infinity, okay, of this guy, I can use this trick. Okay, I can say n is this guy, then n to k minus 1, then k goes to infinity, also n goes to infinity. So replace with this form, because we in sequences we learned that this one have a 0 limit. No, so coming down, this has a 0 limit. Now both conditions were satisfied, so I can say decreasing sequence. Okay, alternating from the alternative. So this is 0 and a is decreasing. Okay, this is decreasing after that e plus 1 over 2. That's fine. No, it's decreasing from the alternating series test as the given series must converge. Okay, let me again emphasize here, most tests those conditions hold for all the terms after a certain term, then it's fine. Okay, because first few finite terms anyway converge. Okay, for any test, if it's condition work for a tail, that means all the terms after certain points is fine. Okay.